In this video, we're going to introduce second-order systems. So, unlike with our first-order systems, for our second-order systems, changes in the system's parameters can change the form of the system response. So with our first-order system, regardless of what value of a we had, regardless of what constant we multiplied the transfer function by, we would always get a system response that had the same basic shape. It might rise faster or slower, but it's always going to look the same. Here, by changing parameters, we can actually change what the response looks like. So before we get into each of those types of response, let's just consider a general second-order system that has two poles and no zeros. So I'm going to draw a little box here, and in our box we're going to put our transfer function. So we're going to have s squared plus as plus b in the denominator and b in the numerator. So of course we can multiply this by a gain, and it's just going to affect the amplitude, it's not going to affect the form. What we're going to see affects the form is our pole location. So R of s is our input, C of s is our output, and of course in the box here we have our transfer function g of s. Now, of course, I know that this is a second-order system because our highest order term in the denominator of the transfer function is s squared, and because of this, I also know that we're going to have two poles. So s squared means two poles for our system. So what we're going to do is let's consider a unit input. So we're looking at our unit step response. So we're saying our input is 1 over s. And we're going to go through in later videos and look at each of the response types. But right here, I want to kind of put them all on the same plot so we can see, sort of compare and contrast what they look like, just sort of qualitatively. So again, let's go through each of these quickly, but we're going to do them in more detail in later videos. So the first response type that we're going to look at is called our underdamped. So our underdamped response type is going to have a relatively quick rise to our final value, but it's going to overshoot and it's going to have to come back down, come back up, and it's going to oscillate about that final value until it eventually gets close enough. And so I should mention that the CF here is our final value. So this is our underdamped. Now, in contrast to our underdamped, we have our overdamped, which is just the opposite. So in our overdamped, we've sort of made it go up so slowly. So let me draw that a little better. It's going up a little slower. So the benefit is it's not going to overshoot and oscillate about the final value. The drawback is that it's taking a longer time to get to that final value. And again, keep in mind that all of these things are just qualitative. We're going to take a closer look later on. So this is overdamped. So then sort of the sweet spot right in between those two is what we call our critically damped. So our critically damped is going to rise as quickly as possible to the final value without overshooting. And so of course these lines are continuing to asymptotically approach as t increases. So this is critically damped in green. So again, that's just one point, which is sort of the transition between underdamped and overdamped. And then we also have undamped. So our undamped case is essentially just going to oscillate back and forth, something like this. So it's just never going to be really getting any closer to that final value. And so I've drawn that a little poorly for that undamped, but we'll come back and we'll look at that later as well. And so these are kind of the main ones we're going to look at, and oftentimes we're not even going to really consider that undamped, but we're definitely going to focus more throughout the course on these three other response types.